give a short talk on some of the results of the PhD. You're more than welcome to attend it next week. I will provide a link if you want to join. So yeah, the PhD topic was about modeling firebrands with a couple fire atmosphere model. There's a lot of people involved in this project. And so yes, there was already some introductions to spotting. This is what we're trying to focus on is on medium and long distance spotting. You see here, I hope it will work, yeah. So a very well developed convective column. At some point the video will zoom in to this part. Yeah, and you see that there is smoke coming from the ground. So this is more than likely to come from firebrands. And the actual fire is right here, so you can have the propagation of the fire that is jumping several kilometers. In Australia, there was a case recorded of 30 kilometers, so it can reach quite large distances. And of course, if you want to model this kind of behavior, you need to take into account all the atmosphere, so that's why we're using a couple fire atmosphere model. Trying to represent firebrands is also quite a hard topic. This is one of the ashes that was found by NIN in Ballarat, which was a city that is 60 kilometers far away from the Grampians wildfire last year. So they're traveling quite a big distance. This is in the Canary Islands. I think it's pine bark scales that were found 15 kilometers far away from the main fire front. So you see that they come in different sizes, different shapes, etc. And so trying to model this is quite important to get an accurate representation of the actual fire spread during a fire event. I said that it's a missing process in couple fire atmosphere models, but not really anymore. There's already some papers describing how to implement spotting into couple fire atmosphere models. So I guess that it's missing in Meson H4 fire, and we're trying to include it within this framework. And the good thing about couple fire atmosphere models is that they were developed with two main objectives. The first one would be to learn more about the actual fire interactions with the atmosphere. And also the second one was to provide faster than real-time predictions of fire. I guess, so this joint PhD was made between the CNRS and the University of Melbourne across two different fire-prone regions, so Corsica and Australia, mixing numerical and experimental approaches. And so the main objective was to find, the problem that we're trying to solve is to find the potential spotting areas faster than the actual fire spread, to try to provide a forecast of where spotting could happen, at which distances, etc. So one of the things that we first tried to do was to follow the literature actually and try to implement the transport of firebrands as individual particles. So what we did is to use Meson H4 fire to obtain realistic wind flows, which look like this one. And then once we have the simulation of the wind flow during realistic fire conditions, we can then calculate the trajectory of the firebrands injected near the plume. And so we did that for two types of firebrands which are commonly found in the literature, which are cylinders and disc, with different initial conditions. So this is, yeah, simulation of the plume during a wildfire event. So we did some tests of aerodynamic models to describe the drag and lift coefficients of the firebrands, also some combustion models that tell us how the size of the firebrand is reducing as a function of the relative velocity, the atmospheric density, etc. And so this lets us calculate the 3 degrees of freedom of the firebrands during their trajectories. So one of the animations that we can see is this one. So here we inject different firebrands with different sizes, different shapes, different initial velocities. And so you see that there are mainly two types of movements. They are either caught in this kind of updrafts, and so they travel quite a long distance. So this is almost 10 to 12 kilometers. Or the other movement is that they are not really caught into these updrafts because of randomness and maybe their size as well, and they tend to fall down quickly as well. And so when you take a look at from the top view and you see what the shape at the ground is, we observed that for the different models, we were getting very different results as well. In the case of the cylinders, we observed that the cylinders were traveling consistently shorter distances than the disk, which can be explained by their less drag that is exerted on the firebrand as well. And when you try to include the combustion, so the size reduction of the firebrand, we observed that for cylinders there was almost no long-range spotting, so everything was happening near the fire. And still for the disk, we were observing some quite notable differences between the different models. So it's really hard to choose a single model to represent accurately the trajectories. So what we thought is that instead of choosing one aerodynamic model, we will try to implement one that is satisfactory in some sense. And so we tried to compare the previous complex model that integrate the aerodynamics and combustion with a new simplified one. And we did it across different topographies. So this is a flat case with no terrain elevations. And in this case, it's a hill. You see here, you see already that the plume shapes are different. The wind at the ground is different. So we expect to have different firebrand ground densities once they are being transported. And so instead of what we said is instead of calculating the accelerations of the firebrand, we will directly calculate the velocities, which is already giving us a reduction in all the calculations. And we said that basically the horizontal motion of the firebrands is given by the horizontal motion of the wind plus a turbulent contribution. And regarding the vertical velocity, is just the vertical velocity of the wind flow minus the terminal velocity of the firebrands, which is telling you how fast they fall on the ground. And so when we compare the two models, so the one that mixes the aerodynamic and combustion with this reduced model, you see here this is the flat terrain and this is the hill terrain. And so the orange contours are actually the complex model and the black gray lines are the reduced model. And so you see already that for example, for the hill case, the shape is not too bad reproduced by the reduced model. The maximum travel distance is also well given, and also the horizontal displacement. And in the case of the hill terrain, there is kind of a dynamic effect here due to the interaction of the plume with the relief or the topography that seems to be caught by both the complex model and the reduced one. And we see that already the distances in terms of travel distance and horizontal displacement are also well reproduced by the reduced model. An interesting thing, of course, is that this reduced model is requiring just 1 second of time step between the integration time. We actually did some tests and it was working at 5 seconds as well, so it's 100 times greater than the actual time step of the complex model, which is running at 0.01 seconds. And so the behavior is the same as well. So see, this is the reduced model, this is the complex one. And so you see that these fragments that are caught in the updraft are similar to these ones. Otherwise, they are just entrained with the flow. And so we still need to include this model into the coupled fire atmosphere model. So the idea was to propose a new method to solve this model. And so the proposed method that we found was to use a Eulerian approach instead of a Lagrangian approach, which looks like this. So you have your individual Lagrangian particles. In this case, you have a Eulerian approach where you're trying to transport a firebrand concentration field across the atmosphere. And so what we did is to inject firebrands with a constant firebrand mass flux during the residence time of the fire in the model. And then when transporting the firebrands using a diffusion advection equation with a terminal velocity as well. And so we did some tests in idealized conditions. So here in gray, you see the smoke. Pink is the actual firebrand concentration field. And then you have the Lagrangian, the Lagrangian modeling. And so the behavior is quite well. We did some comparisons across the flat and the hill terrain that I showed you before. And we see that the Eulerian model is also reproducing this kind of dynamic event due to the interaction with the topography. So we're quite happy about the performance of the Eulerian model. We have similar score skill values, so seeing that the Eulerian model is also giving us similar results to the Lagrangian model at scales of 200 to 400 meters, which is not too bad when you see that the travel distance is almost 15 kilometers. And so the most interesting part maybe is the application case study that we did with Adrian and Nick of a Mount Bolton wildfire, which happened in 2016 in Victoria, in Australia. It was it was a short fire actually, but very intense with tree torching, fire spreading across different types of fields. But most interesting for us is that there were some spot fires that were geolocated by the CFA teams and also timestamps, so we know when and where they happened. And the idea was to reproduce this case with Meson H4 fire and the model to include firebrand transport. So what we did is to have a simulation with 3 nested grids. The first one is at 2,000 meters. Second one is 400 meters of horizontal resolution, and the final one, where you more or less see the relief, the topography, is at 80 meters. And we're having ERA 5 as boundary conditions as well, an initialization of the calculation. So here in blue, I think blue is the observed fire front, and red is the simulation. Oh, yeah, that's it. So at the beginning, the fire is spreading quite fast, so we think that this is due to the spot fires that you see here in yellow. Our simulation is a little bit behind it. So these are more spot fires that were reported by the CFA teams. There was a wind shift that is transporting the fire front towards the east. There was this spot fire that happened here. So our simulation is a little bit behind the actual fire front propagation, of the one that was observed. But actually the main dynamic features, so the propagation to the south and then the propagation to the east, seem to be captured by the model. The other thing that we wanted to check is how the plume looks like. So here we have, I don't know if I can, yeah. Yeah, okay. No. So this is the simulation, and this is the portable radar from University of Queensland that you see here. So at the beginning we didn't have any data. You see that the fire is starting to get more intense as well. The plume is reaching, I think it's almost 2,000, 3,000 meters. I'll try to move it a little bit. Yeah. So now we're starting to get the data from the radar. And what we wanted to do with this one is to check if the plume height was accurately simulated by the simulation, and you see that in our simulation it is reaching 5,000 meters, 6,000 meters for the observation, so it's not too bad. And as well, if you see if you compare the structures and how fast they are moving, they seem to be corresponding quite well as well. So that's a good point for the simulations to be able to reproduce the dynamics of the plume as well. And so finally, what is most interesting for us is the densities of firebrand that I will show here in pink. And you see as well the spot fires in yellow that are being appearing as they were detected. So at the beginning there was this kind of propagation to the south with a large convective episode that is in the model predicting quite a long possible range of transport to the south. Then the intensity of the fire is reducing a little bit. We should start to see the propagation towards the east in some minutes. And there's another more intense convective episode as well towards the southeast, which seems as well to be matching the spot fires that were reported here. Now the fire is still here, sorry, actually, but it's more is moving towards the right. And the thing is that right now the convection is also increasing. You see this kind of pocket of firebrand densities that were predicted by the model. And what is really, we're really lacking in some sense is that a few moments later there's a spot fire that was reported just in the same place, which is kind of magic. But it also tells us that the model is not completely nonsense and could be quite useful actually to predict at least the dynamics of the potential spotting areas. Very interesting thing is that the Eulalia model is executed online, so just as the rest of the simulation, so it's not really taking a lot of time to be executed, and the results are just available as soon as the simulation is finished. And for this particular case, the total runtime was 2 hours to predict an 8-hour fire forecast. So it's taking the mark of having a faster than real-time fire propagation. We're able to identify the main spotting events. So if you remember here to the south, southeast, and then to the east. And also the interesting part is that we can try to get an idea of how intense the spotting event will be because we have densities at the ground level. So we could compare that with how many firebrands could land on a given location. It's the same thing. And so the next steps is, of course, to increase the number of verification cases or simulations with more fires where spotting happened. And the next step, of course, will be to include the ignition of the field bed. So what we're doing right now, but I don't think I have time before next week. No, before next week.
Oh, okay.
Is to have kind of a double threshold stochastic ignition where the ignition of the fire front will only happen if the firebrand densities at a given point is below a certain threshold. In that sense, if it's below, if it's above a certain threshold, it is likely to be very close to the fire front. So it doesn't make sense to have a lot of ignitions just around the fire front. And of course, above a certain threshold so that we don't detect, we don't ignite everything far away as well. And so because it's stochastic and there's a probability, we can also do some ensemble simulations. So in this case, we have 4 different simulations with spot ignition. On peut éteindre la lumière ou pas? So you see the small pockets that are started here correspond to fire ignitions following a stochastic law. And because we're running 4 different ones, each one has a different probabilities. The final contours are also different. So we can also use this kind of simulations to get an idea of what will be the maximum fire propagation or fire spread, and also the minimum one, so we can try to bound as well the possible fire spread during a fire event. So that was everything from me. I'll take any questions.